Ready to get started. Okay, very well. Well, it's a pleasure for us today to have Tim come speak to us about using measurement-induced entanglement to probe the fine structure of quantum states. So Tim, please take it away.
All right. Thank you, Edward, for the invitation. It's nice to virtually visit you guys and hope everyone is doing well. So yeah, as Edward mentioned, I'll be talking about using a diagnostic called measurement-induced entanglement to detect sign structure in wave functions. So this is a work that's pretty much almost completed and done with these collaborators. So here, Jacob and Ising are two postdocs, and Wei-Cheng and Sheng-Chi are two PhD students. Okay, so let me begin with some brief motivation for this talk. So I think all of you have probably encountered sign problem or sign structure in the context of Monte Carlo simulations. So, we think of sign problem, sign structure as a big headache, a computational barrier that renders Monte Carlo simulations inefficient. However, is there a more physical aspect of sign structure? Is it simply a computational complexity aspect, or is there some more physical significance to sign structure? And furthermore, if sign structure is actually something physical, then how do we probe sign structure? How do I distinguish a wave function that's sign free from one that has sign structure without having to interrogate exponentially many amplitudes and check one by one? Are there more observable manifestations of sign structure, or the lack thereof? So let me start first with this question: how physical is sign structure? So recently, there's been a lot of progress showing that sign structure is indeed closely connected to quantum phases of matter and more. So let me first just review briefly what I mean by sign structure, first at the level of Hamiltonians. So we say that a Hamiltonian is sign-free if there's a local basis in which the off-diagonal matrix elements of the Hamiltonian are real and non-positive. If this is the case, then we can map the partition function to that of a classical stat-mech model and use efficient Monte Carlo methods to sample. And here you can see that there's already some ambiguity because we needed to find a local basis in which this holds. So there's a question of, can one always find a local basis in which it's sign-free, or are there cases where there can never exist a local basis where it's sign-free? And so this question of choice of local basis already suggests a connection to quantum phases of matter, right? Which are pretty much defined as equivalence classes up to local basis changes, right? So this begs the question: are there quantum phases of matter with an intrinsic sign problem, namely a sign problem in which there's no choice of local basis in which the Hamiltonian is sign-free, right? And in 2015, Hsieh showed that the double semi on topological order is likely an example of such a phase of matter with intrinsic sign problem. So more precisely, he showed that every commuting projector Hamiltonian, which has double semi on topological order in the ground state, has a sign problem. Okay. So this is a problem for the entire phase of matter, not just the particular model in that phase. And this was subsequently generalized to many other topological orders by Ringel and collaborators. So this is just one example in which there's a deep connection between sign problem and phases of matter. Sign structure at the level of states or wave functions has also turned out to be quite physical. So for example, Grover and Fisher showed that if one takes some Haar random state, which will have volume law scaling of entanglement, and then if you take the absolute value of that state, if you just take the absolute value of each amplitude, then you renormalize, then that resulting state actually only has constant law scaling of Renyi entanglement entropies. Okay, so this suggests that somehow the sign structure is essential in generically giving rise to volume law scaling of entanglement. Okay. And similarly, there's a question that's very related to that of the previous slide. Are there ground states of local Hamiltonians that cannot be transformed into non-negative states via finite depth circuits? Okay, this is like the analogous question for states as it was for Hamiltonians on the previous slide. And indeed, such a sign problem at the level of ground states implies a sign problem for any parent Hamiltonian of that state. And this is because if you have a parent Hamiltonian without a sign problem, then you can just evolve in imaginary time and get a ground state that's also sign free in that basis, right? So in other words, the ground state sign problem is even stronger than the Hamiltonian sign problem. This one implies the other. And a couple of years ago, we were able to show that actually many symmetry-protected topological phases, or SPT phases, have a symmetry-protected sign problem in the ground state. So basically, these SPTs have ground states that no symmetric finite depth circuit can remove. Okay, so this is just a brief and biased survey of showing how sign structure of states and Hamiltonians is something physical. It's more than just a computational problem. Yeah.
So Tim, just a question about that and the third phase, the third point. So
yeah,
when you say so is your expectation that if I have a Hamiltonian that looks like it has a sign problem, but somehow doesn't enter a phase that's intrinsically sign problem full, is the expectation that there's going to be some super non-trivial change of basis that will make it sign problem free? It seems like that seems unlikely, no?
Sorry. Could you repeat the question?
Yeah. So yeah, I understand the way you wrote it. So if you have states that are kind of intrinsically sign problem full, can only come from Hamiltonians that are sign problem full. Right?
Yes.
Yeah. Good. But if I have let's say I have a Hamiltonian that I think is sign problem full, meaning it does enter in some part of its for some choice of parameters, of phase, but it might also enter for some other choice of parameters of phase that's trivial. Or
right.
So is the statement that maybe in this phase there's some kind of in that trivial phase there's a choice of basis that there's a tension between saying that the phases are what determine whether something is sign problem full or the microscopic Hamiltonians, right?
Well, okay. So there are two things here. Yeah, so let me just address one thing which you might not be asking, but let me just make it explicit anyway. So the converse that sign problem for a parent Hamiltonian implies sign problem for the ground state. That one I don't think has been proved to be true, but I also don't know of any counterexample.
Oh, okay. I thought there were. Okay, good.
Yeah. I'm not aware of any counterexample either, but the proof does not follow either. Right?
No, but I'm sure you could make up a counterexample, no, by adding. Well, okay, maybe yeah. I'll try to think about it. But yeah, okay.
Yeah, right. Yeah, it's a good question. I just I'm not aware of any results for that direction. Yeah.
But I think maybe what Luca was asking, maybe I'm wrong, Luca, is you were thinking, oh, suppose I have a Hamiltonian. Can you hear me, by the way?
Yeah.
Suppose I have a Hamiltonian that is in a trivial phase where there's there's no intrinsic sign problem. The question is, does there exist a change of basis which will remove the sign problem for that Hamiltonian? And I think maybe not, right? I mean, I think maybe you're saying there's a good chance you could remove the sign problem for this ground state. Maybe that's related to what you're saying, but for a generic Hamiltonian, just because it's in a trivial phase, doesn't mean you can find some
that's right. Yeah, I think that's right.
change of basis.
Right. Yeah, trivial phase means there exists a choice of basis in which the ground state has no sign problem. But indeed, I'm not sure what can be said about the parent Hamiltonian there. Yeah. Yeah, it's a good point. Okay, great. Yeah, thanks. All right, so let me continue. Right, so, I've given you a taste of how sign structure is somewhat physical. So now there's a question of how do you detect sign structure in a wave function? Okay, so it turns out that for one-dimensional sign-free states that have zero correlation length, Hastings, in the same paper as the double semyon result I showed earlier, he found this very interesting property of such sign-free states with zero correlation length. So what he proposed was to take the wave function and then measure most of the bulk of the wave function in the reference basis, or in the basis in which the state is sign-free. And what he showed is that after measurement, the entanglement for the remaining left and right part of the system decays very fast. It decays super polynomially with the separation between the two pieces. Okay, so in other words, doing measurements in the basis in which it's sign-free cannot generate much entanglement between the unmeasured part of the system. And there's one somewhat rough picture for this result. So the picture is that such wave functions are approximately given by this coherent Gibbs state form. So these wave functions have amplitudes that are approximately Boltzmann weights of some classical Hamiltonian that's local. Okay, and here the classical part derives from the fact that it's sign-free, and the local part derives from this zero correlation length assumption. So if you believe this approximate representation, then it's much easier to see that measuring the bulk cannot generate much entanglement for the remaining system. And that's because by measuring the bulk, you're just fixing a classical configuration on most of the system, and the remaining state, the marginal, is just given by local Boltzmann weights for each A and B piece individually. Okay. So we'll be using this approach, this measurement diagnostic, throughout the talk. So let me just call this measurement-induced entanglement, or MIE. And it turns out this, a somewhat related quantity was already considered a while ago in this paper. Here they consider something called localizable entanglement, which is basically measurement-induced entanglement when you further optimize the measurement basis to maximize the entanglement generated on the remaining system. Okay, so we will not want to do this optimization. We'll just be considering measurements in a fixed basis, the basis in which the state is sign-free. Okay, so yeah, so this is a very interesting result by Hastings. However, it does have this rather strong assumption of zero correlation length. So this talk will be pretty much how to detect sign structure more generally beyond zero correlation. And the central claim we would like to make is that for a sign-free state, entanglement induced by measuring in the sign-free basis must decay at least as fast as existing correlations before measurement. Okay. And the flip side is that any violation of this bound will serve as a fingerprint of non-trivial sign structure. We'll be mainly focusing on quantum critical states. This is partly because it's a relatively new arena for exploring sign structure, and also because in certain contexts we can show that the sign structure can actually constrain the critical data. So this is the central claim that we cannot show in full generality yet. However, in certain contexts, we can make pretty sharp statements. So for example, for sign-free stabilizer states, which I'll define shortly, this measurement-induced entanglement is upper bounded by mutual information. And I'll show you that in certain dynamical models, this can actually constrain the critical theory. And another context in which we can have pretty sharp results are considering qubit wave functions in which A and B are single qubits. And here we can show that this MIE is upper bounded by just a simple 2-point function. So these are the main analytical results, and I'll be providing several illustrations for these results throughout the talk. Okay, so now let me just define this quantity a bit more carefully. So we'll be considering just pure states partitioned into 3 pieces, A, B, and C. And this measurement-induced entanglement between A and B is obtained by measuring C. PC is the probability of getting outcome C. And psi AB, comma C is the resulting state on AB after getting outcome C. And S is just von Neumann entanglement entropy between A and B. So this is really just the average entanglement generated when you measure C. And if I don't specify the basis, then just assume that it's the Z basis or computational basis. So throughout the talk, I'll be comparing this quantity MIE with either correlation functions between A and B or with mutual information between A and B, which you probably know is an upper bound on the square of connected correlation functions. So yeah, in short, I'm comparing MIE with existing correlations between A and B before measurement. And I'm going to see how sign structure informs the relation between MIE and these quantities. Okay, so let's start with just stabilizer states and see what can be said here. So in case you don't know, a Pauli string is just the tensor product of Pauli operators, I, X, Y, or Z. And stabilizer states are eigenstates of commuting Pauli strings. A famous example of this is just the toric code ground state or excited state even, in which the stabilizers are star and plaquette operators. So yeah, we'll first be exploring the properties of sign-free stabilizer states. And one simple property we can show is that a sign-free stabilizer state, for a sign-free stabilizer state, we can choose all the stabilizers to consist of purely X operators or purely Z operators. Okay, and in the quantum information community, this is known as a CSS code. So again, the toric code is a great example of this. The star term is the product of Z operators, and the plaquette term is the product of X operators. The more non-trivial property we're able to show is that for a sign-free stabilizer, this measurement-induced entanglement is upper bounded by the mutual information. So in other words, to get non-trivial measurement-induced entanglement, you already needed to have existing correlations. Okay. And let me just provide a couple of simple examples to illustrate this bound. So first, let's consider just a state on 3 qubits, A, B, and C. And let's say you started out with the EPR pair or Bell pair between A and B, and C is just decoupled. So the mutual information between A and B is 2, and doing measurements on C does nothing. C is decoupled, right? So the measurement-induced entanglement after measuring C is just that of the EPR pair again. So the measurement-induced entanglement is 1 here. A more non-trivial example is a GHZ, or Schrödinger-Katz state, on 3 qubits. So this is all up plus all down. It's a stabilizer state that's stabilized by nearest neighbor ZZ operators and product of X operators. So it's easy to check that the mutual information between A and B is 1. And if you perform an X measurement on the C qubit, then this XC now takes definite value. So you end up with a XA XB stabilizer, and you can just combine these 2 stabilizers to get a ZA ZB stabilizer on AB. So in short, after the X measurement on C, you create a bell pair between A and B. And that bell pair has 1 unit of entanglement. And finally, if you measure the GHZ state in the Z basis, then you just collapse that Schrödinger-Katz to a product state, and you end up with no entanglement left over. So as you can see, in all cases, this bound is satisfied. And it turns out that these simple toy examples are actually all we need to show this bound in full generality for sign-free stabilizer states. And this is because of a very nice structure theorem for stabilizers proven by these guys. So what they found is that if you have a stabilizer state supported on A, B, and C, then there exists local unitaries, UA, UB, UC, that can deconstruct that stabilizer state into a direct product of either 3-party GHZ states, 2-party EPR pairs, or just decoupled product states. Okay, so this is a general theorem for all stabilizers. What we need is a finer structure theorem for sign-free stabilizers. So what we were able to show is that for a sign-free or a CSS stabilizer, these local unitaries UA, UB, UC can be chosen to be CSS or sign-free preserving. That is, they can be chosen to map Z-type stabilizer to Z-type and X-type stabilizers to X-type. And this is a convenient property because now these local unitaries with this property will commute with any Z measurement on C. So this is convenient because now we can just reduce the whole calculation of MIE and MI for this general sign-free stabilizer state to the evaluation of these quantities for these simpler toy states, right? Which I already did on the previous slide. So just reducing it to EPR, GHZ product states now shows that this MIE is upper bounded by MI. Okay, so now we want to explore the consequences of this bound. But before I do that, let me give you an example of a stabilizer with sign structure, which will violate that bound. And the example is a cluster state or a 1D SPT state. And this is the Hamiltonian for the cluster state. It's just nearest neighbor XEX interaction. And so the ground state of this Hamiltonian is a stabilizer state in which all these sets of 3 operators are the stabilizers, and they all take value 1. So for this cluster state, it has a string order parameter that can be obtained by multiplying every other stabilizer so that all the intermediate x's cancel. So you end up with a long string with x's at the endpoints and either z's or identities in the middle. Okay, and since the string is a product of stabilizers, it also is a stabilizer itself, and it takes value 1. And this cluster state also has an Ising symmetry. It's just the product of all the z's being 1. Okay. So now if we choose 2 qubits A and B to be the endpoints of these strings, well, first we can check that the mutual information between A and B is 0, because this is a 0 correlation length model. However, if you measure in the z basis everywhere except for A and B, then now all these z's take definite value, these z's take definite value, and you end up with ZZ and XX stabilizer on A and B, which is just an EPR pair. So in this case, the measurement-induced entanglement is 1. So we just emphasize, even though the mutual information is 0, the measurement-induced entanglement is arbitrarily long range for this cluster state. And this is a direct signature of the non-trivial sign structure of this state. And in fact, this is pretty much the technique we use to show that this cluster state SPT has a symmetry-protected sign problem that no symmetric finite depth circuit can remove. Okay, so that's a brief tangent. So now let me return to the main theme of this this bound we derive for sign-free stabilizers, and what are the consequences. So one interesting area we can apply this bound to are these so-called hybrid quantum circuits that have gotten a lot of interest recently. So these are quantum circuits consisting of both random unitary evolution interspersed with projected measurements done with some probability p. Okay, and so we're interested in the steady states produced by evolving with such hybrid circuits for a long time. So in particular, if the measurement rate is very high, then all these measurements are basically collapsing the state into a product-like state with area law entanglement. And on the other hand, if the unitaries dominate, then they're producing a volume law entangled steady state. And interestingly, there's a critical probability at which you end up with an entanglement phase transition between area law and volume law. And this such critical points have been studied a lot recently. So it turns out that even without unitaries, even if you only have measurements in this circuit, you could already have some interesting critical points generated as steady states. So let me give you a simple example of this. So let's consider just a 1D chain of qubits, and you have 2 types of operations. You either do a nearest neighbor ZZ measurement or a single qubit X measurement. Okay, so the ZZ measurements want to create large GHZ states, and the X measurements want to punch holes in this GHZ state and just produce single qubit X states. Right, so you have this competition between ZZ and X, and it turns out that when both operations are applied with equal probability, you end up with a critical steady state in which the GHZ state has size that has a power law distribution. Okay, and it turns out to be somewhat enlightening to think of this in the Mariana picture. So if you just do a Jordan-Wigner transformation, then these ZZ and X measurements map to nearest neighbor Mariana fermion parity measurements. And now these circuit realizations get mapped to Mariana world line configurations. And so the critical steady state generated from this dynamics can now be understood from all that's known about 2D percolation. For our purpose, we just need to stick with the qubit picture. And the essential features of this model are that first, one, it's sign-free. These ZZ and X measurements, they're sign-free preserving. they map Z to Z, X to X. And furthermore, at all times, the state is just a simple direct product of GHZ states, like shown here. So we already know how to compute MI and MIE for GHZ states. So basically, computing it for this critical steady state is fairly straightforward. So it's easy to check that the mutual information between A and B is non-zero if and only if A and B belong to the same GHZ cluster. And this is also the condition for the MIE to be non-zero. So just based on that, we expect MI and MIE to track each other closely. So for these critical points that are described by conformal field theories, it's useful to plot everything against this cross ratio quantity. That's just a ratio of these chordal distances. And we'll be interested in the regime of small cross ratio, where A and B are basically small intervals that are very far separated. So for this ZZX critical point, we can plot mutual information and measurement-induced entanglement versus this cross ratio on the log-log plot. And as expected, everything has power law decay. And as I briefly argued on the previous slide, the measurement-induced entanglement in the X basis pretty much tracks the mutual information. Both decay with the same power 1/3. And if you measure in the Z basis, it decays even faster. Remember that the Z measurement is collapsing GHZ states. So the only way you get non-zero MIE in the Z basis is if you already have a direct Bell pair between A and B, which has very low probability. So yeah, all this is just to say that the sign-free dynamics gives you critical steady states, which are consistent with this general bound between MIE and MI. Okay, so this is a pretty simple example because the steady state is just a simple direct product of GHZ states. Here's a slightly, yeah, sorry, is there a question?
I just had a question. So you said it's described by a CFT. Do you know which CFT?
Well, it maps the 2D percolation through the Marana picture. So from that, you can actually derive all those exponents I showed you, like the 1/3 and the 2.
I see. So it's the usual percolation.
Yeah.
Okay.
That's right.
It couldn't have been some other non-unitary CFT.
It could have been, yeah, right.
Okay.
Okay, so the example I would tell you about here, we don't know what CFT describes it. So here, as a more non-trivial example, we consider, instead of measuring nearest neighbor 2 Marana parity, we consider measuring nearest neighbor 4 Marana fermion parity. And if you measure each quadruplet with equal probability, then at least you expect that since this dynamics has translation symmetry by Marana on average, then the steady state should be critical. It's not a rigorous statement, but it's just an expectation. And indeed, we find in our numerics that you end up with a steady state with conformal symmetry. And so we can look at so if we map these Marana measurements back to the Qubit picture, these just correspond to either nearest neighbor ZZ or next nearest neighbor XX measurements, which are again manifestly sign-free preserving. So we can again investigate the steady state of this dynamics and look at all these same quantities as before. And similarly, to what I showed you, the MI and MIE in the X basis again track each other very closely with the same power law, which again illustrates this bound that's a consequence of the sign-free dynamics. But I should say that in contrast to the previous slide, we don't really have an understanding of this critical point yet. So it would be nice to pin down whatever non-unitary CFD is describing this. Okay. Okay, so it turns out that we can actually make this bound a bit more formal. So what Li Chen, Ludwig, and Fischer found was that for these dynamical steady states, this measurement-induced power law and the mutual information power law are given by these two quantities, which are the lowest scaling dimensions of certain boundary condition changing operators. So this is a really long story. Let me just briefly say that when you're computing entanglement entropy of a subregion for these dynamical steady states, you can map that to calculating the change in free energy when you change the boundary condition of that subregion. And so the computation of these quantities reduces to calculating some correlation functions of boundary condition changing operators. But for much more detail, I encourage you to take a look at this paper. So for our purposes, we can just translate this bound between MIE and MI into a bound on these scaling dimensions, which is a result of this sign-free nature. So for us, it was quite remarkable that this sign-free condition, which is naively a UV property of some many-body wave function, it actually has consequences in the IR and constrains these scaling dimensions. Okay, so that's a story for sign-free dynamics. And so now what about dynamics with sign structure? Well, as you probably have already expected, these can be obtained from the original hybrid circuits in which you have not only measurements, but also random unitaries. Right? These random unitaries will be introducing signs everywhere. So we'll be considering the critical point in such hybrid circuits, and we'll be considering it for both circuits with Clifford random unitaries, which are defined as unitaries which map stabilizers to stabilizers, or Haar random unitaries, which are just completely random. Okay. So first, for the Clifford transition, we evaluate these same quantities, MIE and MI, at the critical point. And now we find in contrast that the MIE decays as a power law, but a much slower power law than that of mutual information. Okay, so just to emphasize, this condition for sign-free states is strongly violated here. And this is a direct consequence of the sign structure for these steady states. And in fact, it's very tempting to just conjecture that these critical steady states have an intrinsic sign problem that no finite depth unitary can remove. And similarly, for the Haar hybrid circuit transition, we can again look at MIE. We again find that it decays with a power law of 0.29. And since the Haar sign structure is much more complex than the Clifford sign structure, which is discrete, the Clifford signs only involve ±1 or ±I. So since the Haar sign structure is more complex, we expect that the MIE is even more long range, or namely that this bound is even more severely violated. And indeed, that's what we find from the numerics, comparing this 0.29 to, sorry, I guess it was 0.43 on the previous slide. And let me also point out that both Haar and Clifford critical points have mutual information which decay with seemingly the same power law. So mutual information is unable to distinguish the universality classes of Haar and Clifford transitions, whereas this MIE appears to be able to distinguish the two critical points. Okay, so that's all I wanted to say about the effect of sign structure on stabilizer states and these dynamical steady states. And now I'd like to move on to more conventional critical states, critical ground states. But before I do that, let me just pause to see if there are any questions.
Just one quick thing. You said it's tempting to say there's an intrinsic sign problem. Is it?
Yeah.
Is there any reason beyond what you said here, or? I mean, it sounds very plausible. I'm just curious what.
Yeah, I mean, so we didn't push in that direction too much. We, what we did try was to evaluate measurement-induced entanglement where you're measuring in like random bases, right? That would be a poor man's proxy for the local basis change degree of freedom, right? And we found that power law doesn't change at all. And that's pretty much expected because you're doing all these random unitaries at various places. So there should be no reason any local any basis is preferred. So that's all we did. But yeah, I don't know if anything more for that.
Okay, thanks.
Okay, so yeah, let me move on to more conventional critical systems, namely critical ground states of local Hamiltonians. So for this direction, we were able to show that. Okay, so now let me restrict to qubit wave functions where A and B are single qubits. They're not arbitrary intervals. Okay. So what we showed is that for a wave function that's sign-free in the computational basis, then the measurement-induced entanglement, after you measure everything else in the computational basis, is upper bounded by this correlation function, just the XX correlation function. Okay. And this is inspired by an observation in this old localizable entanglement paper. So the proof of this is actually quite simple. So let me just give you a taste of that here. So here's the wave function with amplitudes that are assumed to be non-negative. It turns out that it's convenient to consider as an intermediate step, not measurement-induced von Neumann entropy, but measurement-induced concurrence. So concurrence is a good measure of entanglement for 2 qubits. Beyond that, I think it fails, but 2 qubits is all we need here. And concurrence is defined as this expression here. It's basically taking the time reversal counterpart of the state and then computing the overlap with the original state. So just to give you a little bit of intuition, if you have like a EPR pair, then if you do time reversal, it's invariant. So the overlap with itself is 1. And indeed, the EPR pair is maximally entangled. However, if you have like a direct product state, which is unentangled, then doing time reversal takes you to an orthogonal state. And so the concurrence there would be 0. Okay. But yeah, all you need to know is that concurrence is a good measure of entanglement for 2 qubits. Okay. And this is the measurement-induced concurrence, is just the weighted average of the concurrence over all the measurement outcomes. And so if we plug in just the wave function and expand, in the local basis on A and B, we get this expression here. And now the sign-free nature of the state is really important. So the size here are assumed to be non-negative. And so all the phase factors in this absolute value are coming from the phase factors of these Y operators here. Okay. And so the most that this absolute value can be is if these phase factors all add coherently. Or in other words, if we replace the Y operators by just X operators, which all have the same phase factor, right? So this is upper bounded by just replacing Y's by X's. And this is nothing but just the regular 2-point X correlation function. And given Ising symmetry, half of the configurations vanish here. So it turns out that the YY phases already add constructively here, and you get strict equality, not inequality. And this is already observed in, again, this paper on localizable entanglement. So going back to MIE, it's easy to check that von Neumann entropy is upper bounded by concurrence. And so we can conclude that MIE is upper bounded by just this 2-point X correlator. Okay, so now let me illustrate, let me illustrate this bound in some examples. So let's start out with our old friend, the transversal Ising model in 1D. So this is a sign-free Hamiltonian with a sign-free ground state. And we can evaluate all these quantities, MIE, MI, 2-point function, versus the distance between A and B on a log-log plot. So as expected, everything decays as a power law. And we see that the measurement-induced entanglement tracks the 2-point function, the XX correlator. So yeah, the MIE decays with the same power as the slowest correlator, which is the XX correlator. And so that bound on the previous slide is saturated in this case. As a more non-trivial model, we can also consider the tricritical Ising point. So this is a nice model which has this universality class from O'Brien and Fenley. And for this certain parameter, this model one can check is sign-free. So we can again evaluate all these quantities at this critical point, and the story is similar. The measurement-induced entanglement tracks this 2-point XX correlator, and again the bound appears to be saturated. Okay, so what about critical ground states with sign structure? How do we see violation of the bound there? So for that, it's interesting to consider what's called gapless SPTs, gapless symmetry-protected topological phases, introduced by these authors, I think. So the precise model we consider is if you have a 1D chain of qubits with 2 sublattices, sigma and tau. And we'll be considering the transition between the cluster state model I showed you earlier and a ferromagnet on the sigma sublattice. Okay, so we'll be sitting at this critical point between the cluster state SPT and a ferromagnet. So for this point, it turns out that there are these gapless edge modes that coexist with bulk criticality. And these edge modes are protected by this global Z2 cross Z2 symmetry, just like the gapped cluster state SPT. Yeah, and there's a lot of interesting physics associated with this gapless SPT. But for our purpose, all we pretty much need is the fact that it's not sign-free in either the X or the Z bases. Okay. So what happens if we look at all these measures for this critical ground state? So let's first fix A and B to be on the sigma sublattice. Then we find that the measurement-induced entanglement doesn't decay at all. It's just constant with separation between A and B. Whereas all the other measures like mutual information or correlation functions decay with some power law that can be understood. So yeah, so here the MIE is constant. And it's not that hard to understand this. The argument is pretty much similar to the cluster state MIE I showed you earlier. Basically, the nearest neighbor sigma x, tau z, sigma x operators are still conserved quantities in this model. And so one can, again, multiply them into a string order parameter, run that same argument to show that you get an EPR pair after measurement. Okay. So let me just emphasize that, in this case, the MIE does not decay faster. than the slowest correlation function. And so this is a violation of that bound and a direct fingerprint of the non-trivial sign structure. One can also consider
is there a statement in CFT language of whether it has sign structure or not? Whether a CFT has.
Well, that's one of the open questions I presented to that, and I think, yeah, that's a very interesting discussion that I hope to have a little bit. Yeah.
Okay.
Yes, it's a great question. Let me just get to the open questions. We can go from there. Yeah. Right. So yeah, just to be complete, if you choose A and B to be on the tau sublattice, then now the measurement-induced entanglement it's no longer constant with separation. It does decay with a small power at 0.25, but this power is smaller than that of any two-point correlation function, as can be concluded from this mutual information power 4. So yeah, again, this is a violation of the bound and a fingerprint of sign structure. And I think it's quite plausible that this gapless SPT also has a symmetry-protected sign problem like the cluster state it descends from. Okay, so yeah, now let me just conclude with some open questions. So I motivated this talk by asking for some physical signature of sign structure, and even though MIE is certainly much better than looking at all the amplitudes, it's still somewhat hard to probe experimentally, right? It runs into this post-selection problem where you need to assume the same outcome many times in order to prepare the residual state on AB enough to measure entanglement, right? So this begs the question: is there even more accessible, observable, or multi-parted entanglement measure for probing sign structure? We could not think of it, but maybe there is something. And as I mentioned earlier, it'd be great if there's some way to prove that this hybrid circuit transition has an intrinsic sign problem. I think even more interesting would be to find an example of a 1D critical ground state with an intrinsic sign problem. And as Luca was alluding to, there's this big elephant in the room of basically how to understand all this stuff, like how to understand this object MIE, how to understand sign problem, intrinsic sign problem, in terms of the CFD data, right? The results for the Ising model suggest that MIE is associated with some scaling dimension in the CFD, but how do we make that more precise? So yeah, I would say this is the most urgent question that we would like to think more about. But yeah, let me just summarize what I showed you today. So we want to make the general statement that for sign-free states, the entanglement induced by measuring in sign-free basis decays at least as fast as correlations before measurement. And toward that direction, we showed that for sign-free stabilizers, MIE is upper bounded by MI, and this immediately implies a bound for measurement-driven criticality, at least in stabilizer models. And for Qubit wave functions, we showed that MIE is upper bounded by this XX correlator. And the flip side is that violations of all these serve as fingerprints of non-trivial sign structure. And as some byproducts, we found a critical interacting Majorana measurement model that we would like to understand better. We also found that MIE is able to distinguish these two different critical universality classes. And we would like to make more precise statements about intrinsic and symmetry-protected sign problem, but that's longer term goal. Yeah, that's all I wanted to say. Thank you.
Okay, we can open the floor for any questions for Tim.
I have one question. So for your third point about sign-free spin states, so that was, as you emphasized, for qubit states, right?
Mm-hmm. Yeah.
So what happens if you have more than 2 degrees of freedom? Like, is there a generalization of that?
Yeah, that's a great question.
Trig or
So,
something?
right. So we took one step and considered the 3-state critical Potts chain. And we found that the story is quite similar. So, okay, so this is kind of messy. There's some unnecessary details in this plot, but the short story is that we can consider the generalized X operator for this 3-state Potts model. It decays with some power 0.24 from this numerics. And again, this is very close to the decay of measurement-induced entanglement when you measure the V operator. So this turquoise line here. So I think somehow again, MIE decays with the power law that matches the slowest correlator. And as you said, this is a Q-trick model that goes beyond our bound, right? So I think there's a more general story here that we haven't completely understood.
But do you have a bound on the lattice? Like you derived a bound for the qubit case. Is there a bound for? I'm just trying to understand for qubit.
We do not have the bound beyond qubits, and that's mainly because we don't know of any analog of concurrence for higher than 2-dimensional system, right? Yeah.
I see. But you're hypothesizing such a bound exists.
Yes. Yeah. That's right. Yeah.
Is there a difference for this MIE for like symmetry protected sign problem versus just sign problem?
Well, yeah, that's a good question. So the issue is that we don't know of any. Okay, first of all, sorry, I'm assuming you're referring to still critical states, right?
Yeah, and for the examples you presented, you said they're probably symmetry protected sign problem.
Yeah. We think that this Gapless SPT has a symmetry protected sign problem, and we just are not aware of any 1D model with an intrinsic problem that doesn't rely on symmetry. Right, like we just don't know of an example of that yet.
I see, but then like you would expect like MIE to also tell you something about like higher dimensional systems, and in that case, would you expect there to be a difference?
Right. Yeah, that's true. So criticality aside, if you return to topological order and you ask about SPTs versus topological order, or symmetry protected sign problem versus intrinsic sign problem, there it's probably the case that for the MIE diagnostic, the measurements you're allowed to do need to commute with the global symmetry for the SPT case, whereas the ones that you're allowed to do for the intrinsic case should not matter, right? So that would be the distinction in using the diagnostic there.
Thank you.
Any other questions? Okay, if not, I think we can thank the speaker one more time.
Yeah, thanks.
Thanks so much, Tim.
Thanks, Tim. Nice talk.
Yeah, thanks.
Yeah, it's very interesting.